To finish up the content for this course, we're going to cover 4 more applications of integration, starting today with the area between two curves. First, we're going to learn how to do this, and then you'll have a practice video next. So we talked about this a little in class. Here's the big idea. Suppose we wanted to find the area between two functions' curves. For example, the green area here between the pink curve and the black curve. Since this area doesn't fit an exact geometric shape, and it isn't the area between a curve and the x-axis, we can't use a normal integral or a geometry formula. But we can use an integral. And the trick is we're going to think of this weird area kind of like a Riemann sum. We'll divide it up into a bunch of rectangles, and then we'll add up the area of each rectangle, which is basically just the width times the height. To be a little more precise, you can probably see that the width of each of these rectangles is going to be a delta x. It's a small quantity of x. And if we want our Riemann sum to be really, really accurate, that small quantity of x is going to get infinitely small, and we'll have infinitely many rectangles. At the same time, the height of each of these rectangles is not going to get infinitely small. The height, no matter how many rectangles we use, is always going to be defined by the difference between the pink curve and the black curve. To be really specific, if we take the y value of the pink curve and subtract the y value of the black curve for each rectangle, we would get the height. And if we multiply that height times delta x, this expression will represent the area of that rectangle, and then of course we add them all up. So far, this is just an estimate, but if we wanted to find the exact area using this idea, we would take the limit of the Riemann sum. As we get infinitely many rectangles and their width is infinitely small. But taking the limit of a Riemann sum is really just taking an integral. So here's where we can actually calculate the exact area. The idea is the same as this Riemann sum. A and B represent where the first rectangle starts and the last rectangle ends. Notice in this case it's going to be an x value. You can see them right down here. And then in the inside of our integral we've got dx, which is called the variable of integration. It represents the delta x widths that are getting really thin. And we've got an expression that represents the heights of each rectangle, which in this case f of x represents the y value of the top function, and g of x represents the y value of the bottom function, and we just subtract them to get the area between the two. The right way to do these problems is to think through this setup each time. You should not just automatically subtract two functions because it won't always work so simply, but if you think about what the rectangles are going to look like, you can always end up with a pretty reasonable integral. Let's give it a try. This is the example from class. We're supposed to find the green shaded region, and we're given the definition of the two functions that it sits between. You always want to start by creating a picture. Your sketch doesn't have to have exact points. It does have to approximately represent the shape. And the reason is because you're then going to draw a sample rectangle. Remember, the idea is to think about this area as a bunch of rectangles. I strongly recommend just drawing one of them, but then visually checking, okay, there's one rectangle, I could draw another one here, and another couple on this side. And sure enough, all those rectangles would approximate this area. The reason I recommend just drawing one of the rectangles and then thinking about what the rest would look like is because we're going to use this one rectangle to set up our integral. The first thing you're always going to need to know is the variable of integration, which corresponds to the little width. In this case, our width is a horizontal width, so we can think of it as a delta x. Now that we know that's the width, we can imagine the area being the integral of some sort of height expression times dx, and dx basically corresponds to delta x. How do we get this height expression? Exactly. We're going to create an expression by subtracting the function that's on top, which is the parabola, and minusing the function that's on the bottom, which is this linear function at the bottom. This expression represents the y value up here, this one down here. As you can imagine, a huge common error is to accidentally mess up negative signs because you're subtracting top minus bottom. So I strongly recommend that you use parentheses when you do this. But once you've got that expression, you can go ahead and simplify it. And then the last step is we need terms of integration. We're not supposed to be just evaluating the integral. The answer should be a number for the area. So the terms of integration should represent the x value where the area starts, which I can read off of my graph right here. It looks like it's -1. And then the top limit of integration is the x value where the area ends, which looks like it's 2. Now, in cases where you didn't have a good graph, I would expect you to find those two intersection points by putting these equations into y1 and y2 on your calculator, or by setting them equal to each other and solving for x. Since we've got the numbers and they are accurate on this graph, we can go ahead and take an antiderivative, and then we would plug in 2 and -1 to this function and subtract them. And when we simplify that out, we end up with a nice even number of 4.5. Of course, you can also confirm this number by putting this definite integral into your calculator. Let's try another one. What's the first step? That's right, we start with a sketch and then we add a single rectangle to the sketch. And then we're gonna set up our integral, which should basically take the format of height times dx. And you don't need to write this necessarily, I'm just using it to guide you. So before I can get my expression for the height, we should always just visualize what these rectangles are gonna look like. We've drawn one. The width of the rectangle is our dx, and the height of this rectangle is actually just the height of the top function, which is the square root of x. So we could imagine the integral looking something like this. And that's a pretty simple integral, but there's actually a problem with this. Can you see what it is? Right, so maybe you saw that this height, square root of x, is only the height of this shaded region for the first 2 units. After the first 2 units, when we get in here, the height of the shaded region is no longer the same as the height of the top function because the bottom function starts to cut off the heights. In fact, I could draw a second rectangle here. And you can pretty clearly see that once we get up into this part, this little green rectangle is not defined by the same rule for height that the red rectangle was. So there's 2 solutions. The first solution, and probably the easier one for you to think of now, is we can split this area into 2 sections. And we're going to do that just by drawing a vertical line right here through the x equals 2 line. And I'm going to create one integral for this area, which is actually just this integral right here. And this integral goes from 0 to 2. And then I'm going to add on the integral for this area. And this area is the integral from, well, it starts at 2. And then I'm going to need to figure out where it ends. It looks from the graph like it ends at 4. And the inside of this integral should be the expression for the height of the green rectangle. What is that going to look like? That's right, this second section is going to be the area between 2 curves. So its height is going to be the top function minus the bottom function. And then, of course, the width of each rectangle is still dx. So what's different about this example? To summarize, we had to divide this area into 2 sections, and we wrote one integral for the first part and another integral for the second part. From there, evaluating the integral is exactly what you expect. We take an antiderivative for each of these integrals, and then evaluate each antiderivative at the upper and lower limits of integration. When you simplify, you end up with 10 over 3. So this wasn't terrible, but it actually turns out that there's an easier way to do example 2. And the trick has to do with how you draw your rectangles. So let's start afresh here. Draw another example, or another sketch of the same graph. And this time, instead of drawing our rectangles so they're vertically oriented, we're going to draw them horizontally, just like this. And we can imagine filling up this entire shape by stacking a bunch of horizontal rectangles on top of each other, just like this. And there'd be another one down here. So what's different about this is now, using the same shape of rectangle, we can actually fill up the entire area. All of the rectangles are defined the same way. They all have a little width that's actually vertically oriented. So it's a delta y instead of a delta x. And then their length, or whatever you want to call it, is actually the difference between the first curve and the second curve's x values. Here's what that changes about the integral. Even though we're still just talking about rectangles, we're now going to think of this rectangle as a dy, a small little sliver of y value that's going to get really small, times a length. And the length is going to be the x value of this right-hand side curve minus the x value of this left-hand side curve. Okay, so what that means is we are now going to have an integral with y as the independent variable, which means the expression for length has to use y's, not x's. So that means that I'm going to need to resolve my two formulas for the equation so that they have y as an input and x as an output. Again, that's because I want to use dy instead of dx. And the reason I want to use dy is because I want to orient my rectangles sideways so that I don't have to split this into two integrals. The equations, once you convert them, are actually very simple. X equals y squared is really just another way to write y equals the square root of x. And similarly, if I solve for x down here, we get x equals plus y. Okay, so remember we wanted the second x value minus the first x value for the length. We're ready to set up our integral. It would look like this. And then I can simplify. And I'm pretty close to evaluating. I just need my limits of integration. So notice how your variable of integration is dy in this example. The limits of integration always have to match whatever variable you're using. So these rectangles are going to start on this line, and they're going to keep going all the way up to this height. So this integral is going to start when y equals 0, and it's going to end all the way up here, and you can see on the good graph, they're going to end when y equals 2. Top number is always on the bigger number is on the top. Now we can evaluate this integral by taking an antiderivative. Just treat y like you would normally treat x. And we can easily plug in 2 and 0, which gives us the same answer in a whole lot less work. So we're almost done here, but summarize for me, what was the difference between the two methods, and which one do you think was preferable? Right, the difference between the two methods was we used a different variable of integration, and the second one was preferable because it only required one integral if we oriented our rectangle sideways. So you can probably imagine that choosing the right variable of integration is a really important first step to setting up easy integrals. Take a look at the visual difference between using dx and using dy. When we use dx, you can think of your rectangles as being oriented vertically, which means that your actual integral function is going to be a top function minus a bottom function. If we use dy, we orient the rectangles horizontally, which means your actual integral expression is going to be the right-hand side minus the left-hand side. You can also do this based on the equation. 90% of the time you should just think about which picture makes more sense, but you can also notice that sometimes an equation is easier to work with when you solve for x as opposed to solving for y. If you find yourself wanting to solve for x, it means that you want y to be the independent variable, which means you would probably want to choose dy. Let's do some quick practice. The best way to judge the right variable to use is to sketch both options. So here's your first graph. This horizontal orientation would be if I wanted dy. This one would be dx. In this case, dy is the best choice, and that's simply because in these, all of the rectangles start at the first function and end at the second. Whereas with dx, these rectangles right here are somehow defined by the same function on the top and the bottom, and that's no good. In the second one here, the tip is that you have x as your output, so this would be also a dy. The last one would be a dx. Try 3 for yourself.